This is the entire off-site hardware demonstration that discusses the approach taken towards indigenously designing the system. For the Sakura board, I made my own custom Sakura shield, which I called a cloudy board. It has the provisions for converting the analog values received in the nature and converting them into forms that are acceptable by the Sakura board's ADCs. As we can see, there is a LDR over here which is used to quantitatively determine the amount of light in the atmosphere, uh, and there are provisions for other sensors as well. We have the provision of measuring the voltages at the ADC at the solar panel, as well as the battery, which is a 3.7 volt 2600 mAh lithium ion battery. This is a simple voltage divider circuit with a capacitive snubber. As you can see, the snubber circuit is over here, and we also have provision for measuring the temperature, which is done using a LM35 temperature sensor with again a capacitive snubber. There is a provision for connecting any character LCD, which is based on the Hitachi driver that the Sakura board supports. And another thing that is worth noting is that we have designed an indigenously made soil sensor. It was designed after a few iterations. First we used galvanized iron nails, but they had a tendency to wear out quite quickly, so we used two copper wires in a gypsum or POP mold, and instead of turning or letting the current flow continuously through the wires, we switch the current only when the reading is required. This enhances the life of the probes. Now let's move on towards the power circuit or the power module of the board. As you can see, we have a solar panel that powers the entire setup, but since solar light is not always available and there must be a storage medium, so we have used a battery. Now from the solar panel, the solar panel charges the battery using a buck converter. This is a MC33063A based buck converter. The input voltage at the panel or the MPP of the panel is around 7 volts. So the buck converter converts this 7 volts into 4.8 volts that is suitable for the battery to be charged. And we also have a blocking diode over here in this heat shrink, so that there is no reverse feeding of the current, which protects both the converter and the panel. This converter is about 83% efficient, as we have done in our previous analysis. Now, since the battery is a 3.7 volt battery with a open circuit voltage of about 4.3 volts, it is not suitable to be able to drive a Sakura board which runs on 5 volt USB level power. So I have made a boost converter using a TPS 61222 IC. This converts the 3.7 voltage of the battery into a 5 volt power signal that can be fed to the Sakura board. The efficiency of the IC is very good. It's about 92% efficient, and the switching frequency is about 500 kilohertz, while for the buck stage it is 80 kilohertz. Now we will soon see the demonstration. There is also a very finely cut laser cut acrylic box for the project that can be used to enclose the project very suitably and protect it from environment. Further, on the Sakura board there is a SD card to log the data, and whenever a LAN is connected, the code is written in such a way that it will simultaneously show you the data on the internet connected on a LAN network as well. So we will soon see the entire setup. So this is the software demonstration for the project without the Ethernet enabled. I will do the Ethernet one after this one. So as I told you about the boost stage, now I am turning this system on, and you can see the cloudy it appears, and then then the board keeps on scanning the sensors and displaying the data on the LCD. Mm, yeah. Now you can see the voltage of the solar cell is about 6 volts and the battery is about 4 volts. It means it's charging, and the soil moisture is about 210, which means that it is quite moist. And there is an additional battery saving feature. When I cover the LDR, it will register that it is dark, so it will turn on the backlight. You can see now the light intensity is reduced, so it has turned on the backlight. And whenever I leave it away, it will register that it is day, so it will not turn on the backlight. This backlight is being turned on using a BC547 transistor or an NPN transistor based topology. And after every 5 cycles on the LCD, the average of the data is logged onto the SD card in a CSV, or the comma separated variable or values form, which can be easily exported into any spreadsheet software like MS Excel, which can help you plot the graphs of the data and analyze the situation or the environment throughout the day. The card that is used is a 2 GB NAND card or SD card, so you can log a lot amount of data. And since it is solar powered and has a battery as well, so it can run for quite a lot of amount of time. And with an additional Ethernet connection, you can easily see the data on the internet or at your LAN network if you don't want the data to become public. So it is a very self-contained system. I'll soon give you a demonstration of the Ethernet in a while. And after the entire sequence is completed, the LED blinks to tell you that everything went fine. And there is a lot of error handling code that has been written also, which take care of things like whether there is an SD card or not. Sometimes the SD card is not working correctly, so the LCD will show that the access to the SD card has been denied. So such kind of things has been done. The Ethernet demonstration will now follow. Now the board is over here in my balcony. It has been connected to the Ethernet. As you can see, the light is blinking, and the video that I just showed you was actually in my room, which is quite far from here. The data is sent through the Ethernet connection to this Wi-Fi router, and my laptop has been connected through the Wi-Fi. The data is sent simultaneously, and as before, after every 5 cycles, the average is stored on the SD card. So this completes the exploded sort of demonstration of my project. It is very difficult to show you the demonstration when the project has been combined into the small box, but this gives you a clear idea of how the project works, and hope you like it. I'll show a completed version after this video.